above a half space, this is a ray that goes like that to the observation point. Whereas the other one is a ray that goes like that to the observation point.
But these two rays are going to interfere. So
Oh, they will interfere in this manner. One of them is going to propagate with this phase front. The other one is going to propagate with this phase front. But they are contributions from two very different integrals that you can evaluate separately.
But at the observation point,
Or they will interfere,
look at
of course.
both of them, I'll get an angular dependence.
Right, you would get an angular dependence due to the interference. And here, with one ray coming from here, one ray coming from there, they will interfere. Okay.
So if you put an antenna over just a dielectric, it's going to
interfere. Okay, it's going to interfere. It's going to interfere. One of the things that you might notice in this analysis is that it's not that your D1 has to be large. D1 doesn't have to be large. Okay, you can use a ray optic solution as long as K1RI is large. The observation point is far away. So if you put a microstrip antenna, say, on top of a layered medium, okay, and if you're far away over here, your patch does not have to be far away from the interface. And then you can actually use ray optic solutions to write down the approximation to this ray optic solution. Only the observation point has to be large, not the height of the source above the half space. Or the microstrip patch antenna does not have to be way up of the layered medium. It just has to be close to the layered medium as long as the observation point is far. And these two, of course, will interfere with each other. These two will interfere with each other, giving you the interference pattern that you have. Okay. But actually, if you think about where the stationary phase point is, it's given by this thing over here. And if you were in a complex K-roll plane, where's the stationary phase point? If I go back to the complex K-roll plane, and if this is K1, the stationary phase point is given by this number over here, which is always less than 1. So K-roll S is somewhere over here. It's equal to K1 sine theta I. So what it says is that as you integrate these things along here, along the Sommerfeld integral, you're going to come to a point where the integrand ceases to be rapidly oscillating. Otherwise, in other places, it's rapidly oscillating, but at this point, it's going to slow down. And that's where most of the contribution is going to come from, as you do your numerical integration. Okay? Okay, any other questions regarding this stationary phase point method? If not, then let's go to the other method. Method of steepest descent. It's a more rigorous method. This is like a heuristic method, but the method of steepest descent will be more rigorous.
One question about the coherence of the source.
Right.
Because originally the plane wave extension seems to assume that somehow coherence for the source, right? But it is randomly source. Random source with low coherence can be stationary point analysis value.
Yeah, here we are assuming the source is coherent. The source is coherent, not fluctuating. The source is a steady CW time harmonic source. Okay, in optics, that's not true. It's very hard to generate a source that is coherent for all time. Like all the light bulbs that we have, the sources are actually non-coherent. It will fluctuate. The source actually, like in an antenna in microwave, it's quite easy to run the current through a loop antenna and make it time harmonic. Okay, because the frequencies are very low. But at optics, optical frequency is very difficult to get a source. It is a constant dipole. So you actually have a lot of fluctuation even in the source alone, but we are talking about steady coherent sources. We don't worry about those fluctuations of the sources. that we worry quite a bit in optics, because that is a real world. In optics, you never have a coherent source, unless you do laser. Okay, laser is the source that is closer to be coherent in optical frequencies. Otherwise, all the natural sources that we have are incoherent with the source that is fluctuating. Okay. But when I talk about constructive interference and destructive interference, it's a different kind of interference. I'm just talking about these plane waves. If I think of them as plane waves, they constructively and destructively interfere with each other, even though the source is coherent. Okay, the plane wave as it propagates through space will interfere destructively, and hence it's a beaming effect. So if you're over here, you just worry about this ray. Plane wave becomes ray. Okay, why is that we can approximate plane wave with rays? That is the reason. So we always study plane wave reflections, Fresnel reflection coefficient, and then suddenly we see, oh, people just use ray optics and just draw rays and ignore all the other plane waves. That is the reason. Okay. So let's talk about the method of steepest descent. So if I have a similar integral, but maybe more defined as this integral, not a general g lambda anymore, just this integral alone. And let's assume that it has a stationary phase point or a saddle point such that h prime t naught equal to 0. Okay? And t naught can be anywhere in the complex plane. And if I draw this picture over here, t prime may be something like this, t double prime may be something like this. And then let's assume that t naught is somewhere in the complex plane. Okay? That I'm integrating on some c axis or c contour. And how can I exploit the fact that this thing is 0 over there to expedite my integration? Okay, so some of the heuristic arguments that we use for stationary phase point method may not hold here, because that stationary phase point is actually off over there. And there might be even some poles here, which I call TP. Okay, how can I exploit all the singularities? So what I need to do is actually to first find a path, the stationary phase path that will pass through this point T naught. I'll define to you what the stationary phase path is. Okay, that this path would pass through this stationary point in this manner, and that if I can detour my contour C to this path, then I can exploit the method of steepest descent to evaluate this integral. They assume that instead of integrating along C, I can integrate along P in such a manner that actually expedite my integration, and then I can say that the difference between these two integrals will be the pole residue contribution by Cauchy's theorem. Okay, so what is this stationary phase path? Well, if we have a function h of t naught with the property that h prime of t naught is equal to 0, then h of t can be approximated as h of t naught plus h double prime of t naught t minus t naught squared over 2. Okay, this is just Taylor series expansion because the first derivative equals 0. If I approximate this function in the neighborhood of t naught, this is the approximation. What this says is that this is quadratic. So this motivates for a kind of change of variables that I would invoke a change of variable such that ht minus ht naught is equal to minus s squared to mimic this quadratic behavior. So I try to capture this quadratic behavior with a quadratic transformation. Instead of working with the variable t, I work with the variable s. Okay? So if I were to do this change of variable, then e to the lambda ht by this very simple thing becomes e to the minus lambda ht naught e to the minus lambda s squared. So the exponential function becomes very simple under this change of variables. And then I can say that my I would be equal to, there's no approximation we make at this point, everything is precise and exact. And then over a new contour C prime that I do not know what is as yet, and then ds, dt, ds. Because I did a change of variables, I have to do this. I have to have a new Jacobian. And then f of t, t can be made a function of s now. We have this equation. Okay, t is a function of s, we have this equation. So my f becomes a function of s in this manner. And then I have this thing over here. Okay? I have this thing over here. And I can rewrite this as e to the minus lambda ht naught, a new contour that I do not know as yet what it should be. Okay? And then let me call this just f of s, e to the minus lambda s squared. The good thing about this change of variables is that this function just looks very simple. It just looks Gaussian or Gaussian. Okay, it just looks Gaussian. So let me see what kind of insight I can have by looking at this integrand with the Gaussian function in the exponent.
Is it ds or
Yes.
2s ds?
What is that?
Should that be ds or 2s ds? Because it's a quadratic transformation, right?
I just replaced ht with this, right?
Oh,
Right? Isn't this correct? So this is very nice. It looks very good. But what is the image of C? Okay. But let me look at this saddle point now. This point for which the derivative of this function equals 0 gets mapped to where? Okay. Where does t not map to in this S-plane? If this is complex S-plane, this is real S, this is imaginary S. Where does t not map to on this complex S-plane? This is the mapping. This is a mapping. Under this mapping, ht minus ht naught equal to s squared. If you know complex variables, where does the point t naught map to on a complex S-plane? Yes? No. I just want the point. Tell me where the point. What? Origin. Very good. So this is the image of T naught. That's origin. T naught maps to that point over there. Okay. This is the stationary phase path. It's also called a constant phase path. Sometimes, okay? Constant phase path. On this path, the phase of the integrand does not change. Okay? If I have this path on which the phase of the integrand does not change. So if I look at this new function now, this new function is Gaussian. It's very simple. On which path doesn't the phase of this new integrand not change? No. So I have this constant phase path. Okay, on this path, the phase of the integrand doesn't change. The phase of this function doesn't change. Okay, the phase of this function doesn't change. Okay, now I went through a change of variables. I'm on the complex S-plane now. I'm working with S variable. On which path on this complex S-plane doesn't its phase not change? The real S-axis, right? On the real x-axis, if I keep real s-axis on this path, the phase function does not change its phase at all. So this P must map to this P prime. Agree? So I already helped you with two mappings. The point T naught maps to this point over here. Okay, this is where P naught maps to. And that's where the path P maps to.
Why
Yes?
isn't the real axis right?
Oh, the real axis, when S is real, this is completely a real function. Its phase never change. Okay, so the real axis must be the constant phase path or the stationary phase path. Right, everybody sees that?
How about the imaginary axis?
What? On the imaginary axis, no. On the imaginary axis,
As is pure imaginary.
it's pure imaginary. You're pretty good about that. Okay, also it does not change. So there's actually more than one constant phase path that passes through the point T naught. But this is a path where it exponentially decays, and it's a path that's integrable. The other path is exponentially growing. Function is not integrable along that path. Okay, I picked the path that is integrable. Okay, so now I want you to be able to distort rubber sheets now. Think of this as a rubber sheet. You try to map this to that, and that's what conformal mapping in complex variables are all about. You distort rubber sheets. Okay, how would the path C look like over there? If you think of taking this rubber sheet, take it over there and distort it until it fits in. So the image of C prime must look something like this. Agree? Okay. And then the pole, the image of the pole must look something like that in this thing. Everybody agrees? Think of distorting rubber sheets. Okay, conformal mapping is just that. Everything is continuously deformable in conformal mapping, just like what you did in the Riemann sheet case. Okay, so this is the new path, C prime. So this is where C prime should be. This is where C prime should be. And then on integrating on C prime or integrating on C was no fun, because the integrand can be rapidly oscillating. But if I integrate on P prime or P, it is wonderful, right? It's wonderful because the phase does not change. There's no rapid oscillations at all. And moreover, this is Gaussian in behavior. It peaks here and then it decays on the both sides. So this must be a fun place to integrate. It's like going for skiing, right? You just ski down the slope. Whereas here it's like riding in an airplane in turbulence. The plane just goes around. You don't have to be there, okay? So I would like to integrate on this path and say original path is just integration of this path plus the contribution of the pole. And it's the same as deforming from this path to this path. The constant phase path or the stationary phase path is a very steady path and very easy to integrate. And over here, if I look at this point over here, it's a Gaussian, so it decays like this. And if lambda is very large, it decays even more rapidly. Okay, more and more rapidly. And you're right. If you have picked the wrong one, imaginary axis, as TJ said, you will have an exponentially growing function. So on this two direction is exponentially decaying, but on this two direction is actually exponentially growing. So if you were to ski, you would like to ski from here downward and ski from here downward, and then ski in this two direction. Okay, so this is the ski slope. And if you will imagine this ski slope, what does it look like? Yes? Yeah, it looks something like this, right? And then it looks something like this. Okay? You see? Or saddle, right? A saddle. Saddle. You know what a saddle is? TJ, you know what a saddle is?
Yeah.
Okay, the horse saddle, right? So this is called a saddle point. This is also called a saddle point. Okay. So it's exponentially growing. This is like a mountain pass, right? Mountain pass. Mountain passes often look like this. You try to find the lowest point of too slow and try to go over. Okay? Like this type of. Somewhere in the Himalayas, maybe. I don't know where that is now. And you can tell me, but do you know where that is Khyber Pass?
Yeah, somewhere
Mongolia?
Mongolia.
Afghanistan.
Afghanistan?
Somewhere there.
Okay. I don't remember where it is now, but it's something I learned in geography when it
flat.
the world is flat.
Mongolia is flat.
Oh, Mongolia is a plateau.
Yeah.
So it's quite flat, but it's plateau. So let's take a 5 minute break, okay?